In this video, we're going to talk about optical activity. We're going to discuss whether a molecule is optically active or optically inactive. And we're going to talk about specific rotation and how to get it from observed rotation. We're going to discuss terms such as optical purity and enantiomeric excess. So let's begin our discussion with enantiomers. Enantiomers have a chiral carbon. A chiral carbon is basically a carbon with 4 different groups attached to it. The first group that I drew was a methyl group. The second group was a hydrogen. The third was the carboxylic acid functional group, and the last was an alcohol. To draw the enantiomer of this molecule, we simply need to draw its mirror image. So we're going to draw its reflection across that vertical dashed line. Here, the OH group is pointing towards the left. Now, it's going to be pointing towards the right. Now, let's assign R&S configuration to each chiral center. To do that, using the Kahn-Ingold prelog process, we need to rank the priorities based on atomic number. Oxygen has the highest atomic number. Next is carbon. Here we have 2 carbon atoms, but this is an oxygen versus a hydrogen, so the oxygen will win over the hydrogen. This will be group number 2, 3, and H is always 4. So counting from 1 to 2 to 3, this is going to be the S isomer because we're rotating it in the counterclockwise direction. Now for the molecule on the right, this is going to be group number 1, number 2, 3, H is 4. So if we count it from 1 to 2 to 3, ignoring 4, we can see that we're rotating it in the clockwise direction, giving us the R isomer. So the molecule on the left is called S-lactic acid, whereas the molecule on the right, this is called R-lactic acid. These 2 enantiomers, which are mirror images of each other, they have different optical properties, but they have the same physical properties. So enantiomers have same physical properties like boiling point, melting point, density, solubility. It's the same for these 2 isomers. However, their optical properties are different. The way they rotate plane polarized light is not the same. It turns out that the S isomer rotates light towards the right, and the R isomer rotates plane polarized light towards the left. Now, when it rotates light towards the right, there's a positive sign that is associated with that. When it rotates light towards the left, there's a negative sign associated with that. So this is known as the D isomer. The D standing for dextro-rotatory. The prefix dextro tells us that it's rotating light towards the right. The negative sign is associated with the L isomer, which is known as levorotatory. Hopefully I said that right. But it rotates plane polarized light towards the left. Now, the S isomer is not always associated with the D isomer. The S can rotate light towards the right, or it can do it towards the left. So S is not always associated with the positive dextrorotatory molecule. So sometimes the S isomer could be positive, other times it could be negative, depending on the molecule you're dealing with. Same thing for R. The R isomer could be positive, or can rotate light towards the left. So you can't really determine if it's positive or negative just by looking at the configuration of the chiral center. So just because you have the S isomer doesn't mean you have the D isomer, the L isomer. They're not associated. The S and R tells you the configuration at the chiral center, but the plus or minus tells you how that particular isomer rotates plane polarized light. So S doesn't always rotate plane polarized light to the right. For some molecules, it will rotate it towards the left, which it varies from molecule to molecule. So I want to make sure you get this because this is a typical test question. So remember, S can be positive or it could be negative depending on the molecule. Sometimes it will rotate light towards the right, and other times the S isomer will rotate light towards the left. Same thing for R. For some R molecules, it will rotate light towards the right, and for other R isomers, it can rotate light towards the left. So R doesn't always mean that it's positive, nor does it always mean that it's negative. It varies. There's no direct association between R and plus or R and minus. Now let's say if we have a light bulb. A light bulb, through the process of incandescence, emits light in all directions. So we're going to have light along the vertical axis, light along the horizontal axis, and just going in all directions. This is normal light. Now, if we pass through normal light, if we take normal light and pass it through, let's say like a polarizer, the polarizer is going to act as a filter. Most of the light is going to absorb, but it's going to allow a certain type of light that is in the direction of the polarizer to pass through. So in this case, only the vertical portion of light will pass through. So this is known as plane polarized light. It's been polarized by the polarizer. Now what we're going to do is we're going to pass this through a sample tube. Now let's say this sample tube contains an achiral molecule. An achiral molecule does not rotate plane polarized light. So as a result, as light passes through the tube, the molecules in this sample tube will have no effect on the plane polarized light. So the light will emerge the sample tube without any rotation. So there won't be no rotating this plane polarized light if you have achiral molecules in the sample tube. Now let's see what happens if we put a chiral molecule in the sample tube. So we're going to follow the same process. We're going to take light traveling in all directions. We're going to pass it through a polarizer. We're going to obtain plane polarized light. We're going to filter out all of the unwanted light traveling in different directions, but the light that is in line with the polarizer, that's going to come through. Now, just like before, we're going to pass it through a sample tube. This time, inside the sample tube, we're going to have chiral molecules as opposed to achiral molecules. So if we have a chiral molecule, let's say like one form of the enantiomer, let's say the S enantiomer, this is going to rotate the plane polarized light. So as the light passes through, it will begin to change direction. And so when it emerges from the sample tube, it's not going to be at the same angle in which it was. Notice that it rotated by some degree. Maybe it rotated 15 degrees or 20 degrees, but there was some rotation here. So what you need to know is that chiral molecules, they are optically active. They show optical activity. They can rotate plane polarized light. Achiral molecules are optically inactive. They do not rotate plane polarized light. So how can we determine if a molecule is optically active or optically inactive? Let's work on some examples. So I'm going to draw a few molecules, and I want you to determine whether it's optically active or optically inactive. Feel free to pause the video as you work on these examples. and I'm going to draw one more molecule. So this one's going to be trans instead of cis. So which of these molecules are optically active and which ones are optically inactive? In order to determine the answer, we just got to determine which one is chiral and which one is achiral. Let's start with this one. If you have a molecule with no chiral centers, that is with no carbon atoms that don't have 4 groups, that molecule is going to be achiral. Every carbon atom, there's no carbon atom in hexane that has 4 different groups, so there are no chiral centers, which means the entire molecule is achiral. And if the molecule is achiral, then this molecule is said to be optically inactive. It will not rotate plane polarized light. Now, when you have a molecule that have 1 chiral center, like this one, that carbon has 4 different groups, that molecule is going to be chiral overall. So if it's chiral, that means that it's going to be optically active. This will rotate plane polarized light. Now, when you have 2 chiral centers, like this one, you need to look at symmetry. If there is a plane of symmetry, what you have is a meso compound, and so it's going to be achiral, which means it's optically inactive. Here's another example. Here we have a molecule with 2 chiral centers, and there's a plane of symmetry. So this molecule is going to be achiral, and it shows no optical activity. Now for this one, here we have 2 chiral centers, but we don't have a plane of symmetry. The OH is on the front. Here, this one is on the back. That's going into the page. So this is a chiral molecule, and so this molecule will show optical activity. It will be optically active. Now for the last one, this is not a chiral center. We have a hydroxyl group, there's a hydrogen, but notice that the left side is the same as the right side. So there are no chiral centers for that molecule. Therefore, this is an achiral molecule, which means it's optically inactive. It will not rotate plane polarized light. Now let's talk about some formulas that you need to be aware of. The specific rotation is equal to the observed rotation, represented by the symbol alpha, divided by the path length times the concentration. So alpha without the brackets is the observed rotation, and it's measured. It's an angle measured in degrees. The same is true for the specific rotation, which is in a bracket. C is the concentration of the sample or the solution, which is typically in grams per milliliter. Sometimes it might be represented in literature as grams per 100 milliliters. L is the length of the sample tube. So earlier we drew the sample tube like this. So L is the path length, or the length of the sample tube. That's how far light has to travel through the achiral or the chiral molecules. Now the length of the sample tube is measured in decimeters. So you want to make sure your unit is in decimeters. Now 1 decimeter is equal to 10 centimeters, and 1 centimeter is 10 millimeters. So those are some conversion factors that you're going to need to know when dealing with problems that ask you to calculate the specific rotation. Now the subscript of the specific rotation is the wavelength, and the wavelength, lambda, is in units of nanometers. The superscript is going to be the temperature in Celsius. Now sometimes you may see the specific rotation with a subscript of D. When you see that, what that means is that this is the sodium D line with a wavelength of 589 nanometers. And this particular specific rotation is calculated at a temperature of 25 degrees Celsius. So that's the formula that you need if you wish to calculate the specific rotation of a pure isomer or a certain enantiomer. Now the next thing that we need to talk about is something known as enantiomeric excess. So this occurs when you have both isomers, let's say the R and the S isomer in solution, but they're unequal. One exists in a concentration that's more than the other. Enantiomeric excess can be calculated by taking the observed rotation of the solution or the sample and dividing it by the specific rotation of one of the pure enantiomers. And then you would multiply this by 100%. So if you have the observed rotation of the solution and the specific rotation of one of the enantiomers, then you can calculate the enantiomeric excess with those values. Another way in which you can calculate the enantiomeric excess is if you know the relative percentages of the R and the S isomer. For instance, let's say if a certain sample is 80% R and 20% S. The enantiomeric excess is the difference between the two. It's the absolute value of R minus S or S minus R. In this case, it's R minus S because this is bigger. So it's going to be 80% minus 20%. So we get an enantiomeric excess of 60% in this example. So that's how you can get it in the form of a percentage. Now the enantiomeric excess is equivalent to the optical purity, but in decimal form. So the optical purity is going to be 0.60, which is equivalent to 60%. Now another formula that will help you to calculate enantiomeric excess, particularly if you have a sample where R and S are, let's say, in grams or moles as opposed to a percentage, you could use this formula to calculate the enantiomeric excess. It's equal to the absolute value of R minus S or S minus R divided by the sum of the R and the S isomer times 100%. So using these values, let's say if we have 16 grams of R, 4 grams of S. If we were to subtract these two, we would get 12. We won't get 60%. Nevertheless, 16 is 80% of the total of 20. So as a percentage, these are still the same. But if we were to use this formula, we can still get 60%. So if we take 16 grams of the R isomer, subtracted by 4 grams of the S isomer, and divided by the total, 16 plus 4 is 20, we're going to get 16 minus 4, which is 12. 12 over 20 times 100%. 12 divided by 20 is 0.60 times 100%, which will give us 60%. So that's another way in which we can calculate the enantiomeric excess if we know the relative amounts of R and S in units of, let's say, grams or moles. But if we're given a percentage, we can simply just subtract them directly, and that will give us the enantiomeric excess as a percentage as well. So now you know how to calculate the specific rotation, the enantiomeric excess, and even the optical purity. So now let's work on some practice problems. Number 1, 0.5 grams of a chiral stereoisomer was dissolved in 20 milliliters of solution. The observed rotation measured by a polarimeter was found to be -3 degrees at 25 degrees Celsius using a wavelength of 589 nanometers. The sample tube of the polarimeter is 20 centimeters long. What is the specific rotation of the stereoisomer? Well, let's begin by writing the formula. So the specific rotation is going to be equal to the observed rotation divided by the path length times the concentration. Let's write down what we know. We know the observed rotation is -3 degrees. Now what about the path length, or the length of the sample tube? The length of the sample tube is 20 centimeters. Now we need to convert that to decimeters. Remember, 1 decimeter is equal to 10 centimeters. So if we divide 20 by 10, we get 2. So L is going to be 2 decimeters. Now we're also given the mass and the volume. So we can calculate the concentration in units of grams per milliliter. So if we take the mass of the chiral stereoisomer in grams, which is 0.5 grams, and divide it by the volume of the solution, which is 20 milliliters, this is going to be 0.5 divided by 20, giving us a concentration of 0.025 grams per milliliter. So right now we have everything that we need to calculate the specific rotation of the stereoisomer. So let's go ahead and do that. So first, let's replace the wavelength with 589 nanometers, which corresponds to the wavelength of the sodium D line. So we could just put D for that. The temperature is 25 degrees Celsius, so that's going to be the superscript. And then alpha is -3 degrees. L is 2 decimeters. And the concentration, 0.025 grams per milliliter. 2 times 0.025, that's going to be 0.05. -3 divided by 0.05, that's -60. So the specific rotation of this stereoisomer is going to be -60 degrees. And that's the answer for this problem.